Okay, so in this chapter we will look at direct torque control called DTC and encoder-less operation of induction machines. So here is the overview where we see that this induction machine is being supplied by this inverter, and in doing so we are measuring the currents, and only two of the currents need to be measured because third one we can obtain by Kirchhoff's current law. And then we also need information about the voltages, and that is provided by the switching signals for these three bipositional switches here. And that all this information goes into an estimator, and here you can see listed here that we have measured inputs, stator voltages, and stator currents, and estimated output then is torque and mechanical speed, and that's what makes it encoder-less, and stator flux amplitude and its angle. So the bottom line is that in DTC, our intent is to keep the amplitude of the stator flux within a certain band, and then directly provide the torque that this machine needs based on some outer loops like controlling the speed, as is the case in this overview here. So we can go a little bit further into it. We can see that we have a reference mechanical speed, then this estimated mechanical speed here, and the difference of these two goes into this PI controller, which gives the torque reference indicated by this asterisk sign, and then that is compared with the estimated electromagnetic torque that this machine is providing, and the difference of the two goes into this block, and we'll talk about that in a second. And similarly, this estimated speed that is coming out of this estimator goes into the amplitude of the stator reference flux. So it takes into account this flux weakening region in extended range of speed, and so that amplitude is compared with this estimated amplitude over here, and the difference of the two as the input goes into the selection of which stator voltage vector we should apply to this machine here. So that's basically an overview of this DTC control. So how does this work? What is the principle behind it? Well, the principle is very simple, and that is based on this equation for electromagnetic torque that we can derive, and that is derived in detail in the book. And as you can see here, it depends upon these are all machine quantities over here, but this is the peak amplitude of the stator flux, the rotor flux linkage. When I say flux, I really should be saying flux linkage, and sine of this angle between the stator and the rotor flux linkage, theta sub SR, which is this over here. And all these flux vectors and the angles are defined over here. And as you can see that this is the stator A-axis, this is the rotor A-axis here, and so from with respect to stationary stator A-axis, this is theta sub m. As the rotor rotates, this is changing, and then this is the position shown of the rotor flux linkage, lambda sub r. And the point here to make is that rotor is really a short-circuited cage with a very small resistance of the rotor bars. So this flux linkage, because of the theorem of constant flux linkage, this flux linkage cannot change in a very short time, delta t here. So that's what it's showing here, that the rotor flux linkage at time t is pretty much equal to what it was, one sampling time before. And then and the angle of this rotor flux linkage vector is shown with respect to stator A-axis as theta sub r, and with respect to rotor A-axis as theta sub r with superscript a. And then we have the stator flux linkage vector at this time, and this is what we are trying to change in order to control this torque over here, because as you can see here, it's very sensitive to the angle between the stator and the rotor flux linkage space vector. So this should be a dot over here. We are applying this voltage space vector Vs arrow times this delta t. For this particular time, we are applying it and we try to apply it perpendicularly here, let's say, and so it is going to change the position of the stator flux linkage space vector, but not the amplitude very much, because these two vectors are, this one and this one, are perpendicular to each other as much as possible. Okay, so that's basically the idea of this direct torque control in an induction machine here. So let's go through the basic equations that this is based on. And again, these are derived in great detail in the book, and we shouldn't really be going through them. So this is the equation for the stator in terms of the stator's voltage space vector, the current, and the flux linkage, right? So we can write it in this form here, where this is at time t is equal to at previous time step, and then the integral of this quantity here from the previous time to the present time over here. So this is a vector, so it has an amplitude and it has an angle theta sub s over here. So that's the equation for stator flux linkage space vector. And we can also then calculate the rotor flux, which depends upon this stator flux space vector, which we have just computed, and also the stator current space vector, which we can get by measuring the stator currents as shown in the previous diagram here. And again, this being a vector, it has an amplitude and it has an angle, this theta sub r. And as you recall, the definition of theta sub r with respect to stator a-axis. And then we can write the equation for estimating torque, which turns out to be of this form over here. So as you can see, this is the imaginary part of lambda sub s conjugate and I sub s over here. Okay, so that allows us to compute the electromagnetic torque without having to actually measure it, which will be very expensive to do. And so now the next thing is we want to make it encoder-less, so we have to estimate the mechanical speed. So as you can see here, that omega sub r is really the time rate of change of theta sub r, and theta sub r is in an interval, this interval over here, which we have to judiciously pick. It's equal to theta sub r at time t minus theta sub r at the previous time over here, divided by that time interval over here. So that's theta sub r, and this omega slip is the rotation of the rotor flux linkage space vector with respect to the rotor a-axis. Okay, and that is given by this expression over here. Again, all these things are derived in the book, so I will not belabor that point here. So what is omega sub m? Is really omega sub r minus omega slip over here. So that's omega sub m, and that is the speed at which the rotor is rotating, and mechanical speed, but in radians, electrical radians per second, all right, electrical radians per second, and then mechanical speed in actual mechanical radians per second is obtained by multiplying omega sub m by 2 over the number of poles that we have. Okay, so we have all the equations that we need. So now we have to decide, in order to control this electromagnetic torque, what voltage space vector we should apply. So we know that from an inverter, we can only get 6 active vectors shown here, V1, V2, so on like that. And then we have 2 zero voltage vectors, where all the switches are either in the up position in all 3 poles or they're in the down position here. And we divide them into 6 sectors as shown here. So between this line and this line here, we have sector 1, and we can similarly show the other sectors. So here we should think about what voltage space vector we should apply depending upon what we need to do with torque and with Stator flux amplitude. So the bottom line is that we would like to maintain the torque in a band here. So let's say this is torque, electromagnetic torque. Similarly, we like to maintain this lambda sub s amplitude within a band over here. Okay. So depending upon what is needed, we will apply the appropriate voltage space vector. So let's say that we are in sector 1, and let's assume that this voltage is let's see here, this lambda sub s right now. Let's just take it as in between here, but it could be argued for any other position of lambda sub s in within this sector 1. But the bottom line is that we are describing it for sector 1, and this can then be applied to other sectors, and within a sector, different positions of this Stator flux linkage space vector. So let's say, given this position here that we are assuming, these are the 6 possible active voltage vectors we can apply for this particular time step that we judiciously choose. So you can see here that applying any of these voltage space vector for some particular time interval delta t would have certain impact, and that is that we can see here, that if we apply V1, it's not going to change the angle of the Stator flux linkage space vector, but it's going to increase the amplitude. Whereas if we apply V3, well, it's going to change, it'll increase the angle in a counterclockwise direction, and will also change the amplitude of lambda sub s. Whereas if you apply V2, then you'll see that it again changes the angle in the counterclockwise direction, but will decrease the amplitude of lambda sub s. Okay, so with that knowledge, we can very easily, actually, I probably should have talked about it with this slide, but it's just you can see it more clearly here because all the information is here in the single slide. So you can see selection of Stator voltage space vector, and if you want to increase the electromagnetic torque and you want to also increase lambda sub s amplitude, it makes logical sense to apply V3 as I explained earlier. And if you want to increase this torque but want to decrease this, then it makes sense to apply V2. Similarly, you can talk about the effect of V4 and V5. But like I mentioned to you earlier, that we have other possibilities of applying zero voltage vectors, especially if you are within this electromagnetic torque band and you're within this flux linkage amplitude. Did I say torque band? I meant to say hysteresis band. And similarly, if you are within this hysteresis band of lambda sub s amplitude and torque, electromagnetic torque, hysteresis band, if you're within that, then maybe you want to apply zero voltage. Okay, so that's the effect of zero Stator space vectors are shown here. You're not applying any voltage for a certain interval delta t. So what's going to happen is that this you're not applying any change in the Stator voltage. So this sign should really be approximately equal to 0. So the change in the position of the Stator flux linkage vector would be essentially 0. So theta sub s would not change. Okay. what is happening to theta sub RA? Well, that with respect to A axis, that is also not going to change very much. So this is also equal to 0. Okay. So again, this rectangular you see is approximately equal because, as I mentioned earlier, rotor is a short-circuited cage. So with respect to its own axis, capital A, this rotor flux linkage is not going to change. So this is going to be essentially 0. And so theta sub, the change in the rotor flux linkage space vector is really made up of these two changes. See the rotor is rotating, so this theta sub m would change. So rotor A axis was here at previous time step, and rotor A axis is over here. So there is a change in this mechanical angle, but this essentially is 0, this part over here. So you can see that this again is approximately equal to theta sub m, because this part is essentially 0 here. Okay, and then you can see that sine of theta sub SR is really the difference of these two over here. But for small values of angle in radians, you can say the sine is the same as the angle itself here. So you can see that this is approximately the same. So this electromagnetic torque is some coefficient k times, and we had this equation in detail, but if you assume that the amplitudes have not changed very much, then this electromagnetic torque is the difference of these two angles here, and you can see here that since this is equal to 0 approximately, and theta sub r is equal to minus delta, change in theta sub r is minus delta theta sub m from this equation here. Well, change in theta sub r is this here, but there's a minus sign here. So that's why we get this equation here. Okay, so you can see that there is a different, this electromagnetic torque would change a little bit if we apply 0 stator voltage space vector here. So that's what would make this electromagnetic torque move up and down and like this here. And we want to make it within this band here, right, for electromagnetic torque here. So here is a Simulink block diagram, which we should go through in detail. It's a fairly complex diagram, but here it shows that here is the reference speed mechanical, and let's say you want to keep this constant. So if that is the case, this change here is equal to 0. You don't want to make any change here. And there is a step change in load torque here. So we have done this in other chapters as well. Well, there is a change in load torque as a step, but we want to keep the mechanical speed constant. That means this change is 0, or you have this reference mechanical speed here. And so here we can see that all this information that I mentioned to you earlier goes into this estimator block over here, and from here we have we estimate the mechanical speed, and that goes into the reference speed compared with the reference speed, and using this PI controller we compute the electromagnetic torque reference here, and that is compared with the electromagnetic torque estimated in this block over here, and and same thing we do with the rotor, the flux linkage, lambda s, which is the reference coming in here, and then we also have the rotor flux linkage estimated here, and the difference of these two here, all goes into the selection of the voltage space vector to this machine model. So when I say actual, it's really not an actual machine. Here's the model of the actual machine here. So the results we see in this slide here, where we have this reference torque coming in and then the estimated torque over here, they pretty much have the same waveform in both cases. And then we have the reference speed is in red, which is constant, and then you have actual speed in blue here, and this is the estimated speed over here. Okay, so they also look pretty much the same, and this is what's happening to the Stator flux linkage vector amplitude over here, and you can see that this red is the estimated value, and a reference value, I should say, in red, and then estimated value is in green here. So that's within a tolerance band, you can see here. And you can see that both rotor and stator flux linkage space vectors, they are pretty much, the amplitude is constant, and maybe a slight jitter because of the thickness of the hysteresis band, and here the position is plotted in XY coordinates, alpha and beta coordinates here. So this is basically it, and this is quite common way to control induction machines. If you use this approach, one of the drawbacks, as one may say, is that the switching frequency of the inverter is not constant. But there are other ways to get around that as well. So bottom line is that whether you use vector control, as we have seen earlier, or you use DTC, we ought to be able to control this machine in terms of its position, then its speed, and by controlling the electromagnetic torque that this machine generates to compensate for the load torque. So thank you very much. Okay, so David, discard annotations, right?
Yep.
Okay, discard.